Hello. In this discussion, we're going to address the interplay between linear transformations and matrices. So the first principle that we're going to discuss is if you give me a matrix, then I can build you a linear transformation. We're going to review this statement, and then we're going to address this statement. If you give me a linear transformation, then I can give you back a matrix. Okay, so let's consider this example in which we have a matrix with 4 columns, and we decide to define an operator from C4 to C3, meaning that because this matrix has 4 columns, we're gonna exploit the operation, the matrix operation, matrix vector multiplication, and then we will be able to output a vector in C3. So we define the function taking a vector in C3, a vector x comes in, and then the definition of that function is precisely the matrix vector multiplication. So we remember that here in this example, this matrix has 3 rows, 4 columns, and the vector has 4 rows and 1 column. So the output, when we multiply this, we think of this as matrix multiplication. This whole product is going to have dimensions 3 by 1, and that's the explanation of why the input is a 4 vector of length 4, and the output is a vector of length 3. And so specifically, we have this matrix product where the entries of x are denoted here by x1, x2, x3, and x4. And by following the definition of matrix vector multiplication, the product of this matrix times this vector is no other thing than a linear combination of the columns of the matrix. So the coefficients in these linear combinations are precisely the entries of these vectors. So this entry is x1. Here's x1 multiplying column 1 of the matrix. So if you will, we can call this a1, and this will be called a2, and this here will be called a3, and a sub 4. Right? So this is nothing new. This is simple matrix operation. So if we continue the operations here, so we know that what happens, each member of this linear combination is a scalar multiplication. So multiplying the scalar x1 and times every entry of vector of the first column vector gives us 3x1, 2x1, 1x1. If we do the same for the second term here, we have minus x2, 0, and 1x2, and then we move on to the next one, which would give us 8x3, 5x3, and 3x3. And last but not least, we have 1x4 minus 2x4 and minus 7x4. So we could go ahead and write in a last step here, we can write this as a whole vector. So we would have the first entry would be 3x1 minus x2 plus 8x3 plus x4. The second entry would be 2x1 plus 5x3 minus 2x4, and the last entry would have x1 plus x2 plus 3x3 minus 7x4. So remember, this all these steps are the steps defining this operator P of x, right? So P of x, an x vector in C4 comes in as an input, and the output is a vector with 3 entries. And you can see how this this is no other thing than P of x, right? So by construction. And so the entries of P of x look exactly like a linear system of equations, if you will. So this simply connects the form of this transformation to something we're extremely familiar. This is exactly how we started, how we began learning about linear algebra, with expressions that look like this. The variables x1, x2, x3, and x4 here appear in a linear fashion. And so this illustrates how, given a matrix, we can define a linear transformation. So in a bit of more formal way, we say, suppose we have a rectangular matrix, and we define the matrix product A times X, where X is a vector that matches, it has as many entries as the number of columns of this rectangular matrix. And so this product is what we actually define as a transformation acting from Cn, the number of, where n is the number of columns, mapping Cn into Cm, where m denotes the number of rows of the given matrix. So we're given a matrix, then we can define by matrix vector product a linear transformation. But is this something that is this going to do it? So it's not too difficult to verify that this indeed, what we want is to verify that this is a linear transformation. So suppose, let's say that we have x and y being vectors in Cn. So now let's check what happens to the transformation T acting on the sum, the addition of x plus y. So by definition, this would be A multiplying x plus y. And then this follows really from properties of the vector space of matrices, or properties of matrix vector multiplication, because we know that by properties of matrix vector multiplication, this becomes A multiplying the vector x and A multiplying the vector y, and each of these is indeed, by definition, the operator, the map acting on x, and then the map acting on y. So we started with the transformation evaluated at the sum, and then we obtained that that indeed becomes the sum or addition of the transformation evaluated at each individual vector. And then if we assume that we have a scalar, then we can check what happens if we evaluate, say, the alpha y, if we evaluate the map, the linear transformation at that product of alpha times y. So this would be multiplying the matrix A times alpha y. Alpha is a scalar, so we can write that on the left side, and this becomes alpha times ay, which is no other thing than alpha times the transformation evaluated at y. So it's rather straightforward to verify that using this definition, indeed, this map is a linear transformation. So now we move to the other statement. So if you give me a linear transformation, then I can build you a matrix, okay? And so let's see how this statement, what's the basis of this? Well, you could be a little more formal and say, suppose we have a transformation from Cn to Cm, and if that is the case for a given transformation, then there exists, or there is, a rectangular matrix such that when we multiply that matrix by an arbitrary vector x, that product is exactly equal to evaluating the given transformation and that vector x. And so this relies on evaluating the linear transformation at each of the basis elements of Cn. So remember the columns of the identity matrix, those are called the standard unit vectors, and here they're named as E1, E2, all the way through E sub n. And we evaluate the transformation at each of those standard unit vectors, and that evaluation is what we would call a column of the matrix that we're in the process of building, of constructing. That's exactly how we construct that matrix. Take the transformation, evaluate the transformation at the standard unit vectors at the columns of the identity matrix. That's going to give you a column vector, and that is the column vector of the matrix we are building or constructing. So we're going to put all those columns together, and that's how we define such matrix. So let's work this example. This is the definition of the transformation. Here we're working with C3, so let's evaluate its transformation R. Evaluate it into E1. So this means that we're evaluating this and with the vector 1, 0, 0, 0, and that means that we substitute in this definition of transformation, right? So x2 and x3 are equal to 0. So here we have 1, minus 1 plus 0 plus 0, and then minus 1 plus 0 minus 0, and then x3, which is 0. Okay, so that gives us a vector. This vector is in C4. We're simply evaluating, substituting there. So now if we evaluate transformation R into E sub 2, by doing that evaluation, so remember for E sub 2, x1 is 0, x3 is 0, but x2 is 1. So we obtain 0 minus 1, 0, and then you can easily see here how we obtain the other entries. So that leads us to the vector minus 1, 1, 5, and 0. And lastly, for the last standard unit vector, we evaluate that into this transformation R. In that case, x1 and x2 are 0, x3 is 1, and that gives us the vector 1, 1, minus 3, 1. Which means that in this case, the matrix associated with this linear transformation would have 3 columns, and these columns are 1, minus 1, minus 1, 0, minus 1, 1, 5, 0, and then 1, 1, minus 3, 1. So this would be the matrix associated with this linear transformation, which was obtained by evaluation of the standard unit vectors into the definition of this map or this operator.